We now start exercise 1 with the assumption that we have a Kremer-Lundberg process represented by its random walk representation. And what we start by doing is we introduce a measure, mu tilde, defined by the fact that it is an exponential shift of the distribution of each of these random walk increments. So let mu tilde be defined as an exponential shift of mu where r here is the adjustment coefficient. Now, just a few more assumptions. We also assume that the net profit condition is satisfied. So let's just write it here, net profit condition satisfied. And that means that the premium should exceed the expected claims. So C should be greater than the expected arrivals. We expect lambda arrivals multiplied by the mean value of the claim size. Okay, so what we are going to do now is solve A, where we are asked to check that mu tilde is a probability measure, and we are also asked to consider whether Zi has negative or positive mean under this new measure mu tilde. So we want to show that mu tilde is a probability measure, and 2, we want to check, so we want to see is the expectation of Z under mu tilde positive or negative. Because the thing is, the expectation of Z under mu is definitely positive due to our net profit condition. And therefore, that will make the Rouen probability smaller, strictly smaller than 1. However, if we are able to show that under our shifted measure, the z's here, the increments in the random walk, if we can show that under the shifted measure, these increments are negative, then are expected to be negative, then that actually means that under the shifted measure, we expect our capital process to have a negative drift, in which case you will most definitely have Rouen with probability 1. So we want to arrive at the conclusion, at least, that under this shifted measure, our process will have negative drift and therefore achieve Rouen with probability 1, and therefore it will make sense to simulate stuff under this shifted measure. So let's try to show first that mu tilde is a probability measure. Now, mu tilde is a probability measure if it satisfies 3 things. If 1, mu tilde of the empty set is equal to 0, and 2, if there is sigma additivity, or also what some people call countable additivity, and 3, if mu sigma, if mu tilde integrates to 1 over its entire domain. Now, the first 2 here are satisfied since mu satisfies these two. So since mu is a measure, then these two are automatically satisfied. Because mu is a measure, then mu tilde is also a measure. So the only thing we really need to check is whether mu tilde is a probability measure. So we need to check number 3. And we do that by calculating this thing here. So let's do an abstract change of variables, since we know that d mu tilde is equal to, I have to have a y here, and since we know that d mu tilde is equal to this thing up here, so this is equal to the integral from minus infinity to infinity of e to the minus ry with respect to mu. And since mu is the distribution of Z1, we just have that this is actually the moment generating function of Z1 evaluated in the value minus r. And well, what do we know about the moment generating function in minus r? We do know that r is defined, so just recall that r is defined as that number which satisfies the cumulant generating function and minus r is equal to 0, and the cumulant generating function is equal to the logarithm of the moment generating function. Therefore, well, this thing here is just e to the cumulant generating function in minus r, where we know that the exponent is then 0, so this is equal to 1. We therefore have that mu tilde is in fact a probability measure. Our second question now is whether or not the expectation of Z1 is negative. And as we argued earlier, we actually wish to show that it's negative because that would be nice. So let's just try and see if we can achieve that. So this is by definition equal to the mean value, equal to the integral of y with respect to the measure in question, which is mu tilde. And again, we use the abstract change of measure. I mean, some people call it abstract change of variable, the push forward theorem. It depends on where you come from. But anyways, I just call it the abstract change of variables. So you have y and multiplied by e to the minus ry with respect to mu of y. And what you then see here is this is just the mean value of Z1 multiplied by e to the minus r Z1. The question is whether we can say something smart about this in terms of the moment generating function or the cumulant generating function. So let's just go with the moment generating function first and recall that for the moment generating function, if you differentiate it with respect to alpha, so if you have the mean of e to the alpha Z1 and you differentiate it with respect to alpha, then what you get is mean to the Z1 e to the alpha Z1 if all the moments and so on that you need to be well defined are well defined. So what we actually have here is the derivative of the cumulant generating function of Z1 evaluated in minus r. Now, is this smaller than 0 or greater than 0? Well, I'd like to argue that it is smaller than 0. And the way we do this is by considering how this relates to the cumulant generating function, because we know some things about the cumulant generating function's behavior in minus r. So if we just try to differentiate the cumulant generating function with respect to alpha, then what you actually see is what we then want to do is we want to differentiate. So note that the derivative of log of the moment generating function with respect to alpha is just 1 divided by, so 1 divided by the moment generating function multiplied by the inner function's derivative, which is derivative of the moment generating function. And that also then will imply that we have an expression for the moment generating function in terms of for the derivative of the moment generating function in terms of the derivative of the cumulant generating function and the moment generating function. And now note in particular that if we want to consider how this thing behaves in minus r, then wow, we are lucky, because you then have the cumulant generating function's derivative in minus r multiplied by the moment generating function in minus r, which we know already is equal to 1. So the moment generating function in minus r is equal to 1. And our only question now is, well, is the cumulant generating function, well, does it have negative slope or positive slope in the value minus r? And for this, it's very useful to recall the graph that Jeffrey often draws during lectures of the cumulant generating function, which is convex, hits the x-axis in minus r, and hits it in 0. And due to this construction, the cumulant generating function in minus r is always negative. So therefore, you have that the mean value of the random walk increments under this shifted measure is always negative. And therefore, our random walk will have negative drift under the shifted measure, which is very fortunate in terms of what we would like to simulate. Just before we finish this off, let me just mention that these formulas down here are actually quite useful. So keep them somewhere in the notebook in case change of measure methods turn up during the exam.